To everyone for taking the time to join me today on our webinar to discuss compressor and turbine modernization and the benefits of having an integrated control system and optimized actuation package implemented at your plant. My name is Mike Murphy and I'm the Rotating Equipment Product Manager for REXA, and I'm happy to have the opportunity to introduce our unique REXA actuation technology to you. We would like to start with a brief background of the presenters today. For my personal background, I have 23 years of experience focused around process controls, where I've worked as an application engineer, as an account manager for a manufacturer's representative that was focused on INC solutions, a partner in a small engineering, integration, and field services company in New England, and most recently with REXA as power industry manager, marketing manager, and rotating equipment product manager. For those of you not yet familiar with REXA, we are an industry-leading manufacturer of highly engineered actuators that are used in critical process control applications. I will be co-presenting this webinar with Emily Hoop, Marketing Manager for Compressor Controls Corporation, or CCC for short. Say hello, Emily.
Hello, everyone. Thanks, Mike.
Emily has 13 years of industry experience, where she has previously worked at Emerson Process Management as an application engineer, as the refining industry manager, and as the sliding stem valve products marketing manager. And CCC is a worldwide leader in delivering engineered compressor control solutions. For some of you attending, you may have some previous experience with REXA actuation technology or with CCC's approach to delivering improved turbo machinery solutions. Or perhaps you have experience with both REXA and CCC, in which case this will be a great refresher. For those of you who are new to CCC or new to REXA and are looking to gain a better understanding of our deliverables, I'm confident you will find the webinar to be informative and that it will provide valuable insight on how we can help improve your plant throughput and reliability. To begin, let's review the webinar agenda. We will begin the presentation discussing market trends and business objectives that are faced by various manufacturing industries as it relates to optimizing their process controls. At the center of this discussion is turbo machinery. The webinar will focus on some of the most common challenges found at the plant level in regards to improving reliability, optimizing performance, and reducing maintenance. We will discuss the importance of advanced control strategy, measurement, and actuation in detail, and we'll discuss the areas in the process where you can expect return through modernization and upgrade of your equipment. We will then present a brief case study detailing a successful CCC REXA upgrade and the results generated for that particular facility. Finally, we will wrap up with a brief questions and answer session. The expected time for the completion of the webinar is approximately 45 minutes. Please share your thoughts throughout the webinar, and remember, you can send your questions in via the chat functionality. With that, I will turn it over to Emily Hoop to begin the webinar.
Thanks, Mike. I'll start with the market background, and this is what we've all been experiencing, so it's just a bit of a summary, but in today's volatile market, we've all been feeling the pain of lower oil prices for longer than before. Industry statistics are predicting that by 2020, half of the workforce will be retiring, and industry experts have even coined this as the great crew change. So we're all challenged and tasked to do more with less. This means we have to be smart in the way we work so we can still achieve high-level business objectives with fewer people. The goal, of course, never changes, and that's always to be profitable. That means reducing costs and increasing revenue. Each plant, of course, sets their targets to improve, and that may depend, varying on your industry, depending on your industry, infrastructure, maybe what type of standardization efforts have been in place, or even the age. So how you personally impact these goals in your daily job is what we'd like to kind of focus on today in more technical detail. In the end, of course, it's up to you, the people on the ground, to set priorities and execute these objectives. So in this webinar, we'll cover some strategies to achieve safer and more reliable operation and better performance while reducing maintenance. The focus, like Mike mentioned, is around some of the most critical equipment in your facility, and that, of course, is turbomachinery. To ground everyone before really jumping into how to achieve your plant objectives, I'd like to define what we mean by turbomachinery. The train makes up both the driver and driven equipment. The driver could be a steam turbine, gas turbine, or a motor, and the driven equipment is typically a compressor, but it could also be a pump or a generator. Turbomachinery is at the heart of your process. Efficiency and availability of these machines directly impacts your bottom line. So just like any control system, turbomachinery control consists of measurement, the control system itself, and the control element. A good turbomachinery control system keeps the process steady and provides protection to the machinery as well as the downstream processes in the event of an upset condition. To understand the importance of these elements working together, you can think of the following analogy. In a car driving down the road, you're the one taking in the measurements of your car between the lanes, the levels of gas and oil, the response of the tires on the roads. The control system would be analogous to your brain, making the decisions about what to do next. Do you step on the gas or slow down? The actuation responds just like pedals in a car, and they better work when you need them to in order to stay safe or get to your destination on time. The response of your car is the feedback from the process. Did your tires maintain traction? Did your speed increase when needed? Ultimately, did you stay on the road when the deer jumped in front of you? Or did you have to pull over? These elements are all working together, sometimes so fast you don't even think about it. The same is true for your turbomachinery control. Knowing where you need to go is the blueprint for how you design your system to work just the way you need it to. The following examples are typical signs of poor control systems: unplanned process trips where specific limits are exceeded, unstable process variables when the set point can't be achieved quickly, and lastly, constant recycle. Addressing these conditions with turbomachinery control can lead to improved efficiency and availability. So how do we solve these challenges? We're going to dive into how REXA and CCC have teamed up to do just that. The CCC-REXA modernization package ensures that all the critical turbomachinery control elements are working together seamlessly. How we do this is through advanced control, measurement, and precision actuation. Together, these technologies help you to execute the plant priorities. Starting with advanced control. This, again, is the brains behind the turbomachinery control solution, just like our car analogy. Here is where you define how you need to operate to meet your plant objectives. By setting this up right, you can optimize performance in a number of ways: maximize availability, increase production, reduce energy costs, and automated startups. After reviewing the challenges associated with each objective, I'll also provide a few details of key technologies required to get the results you need. Beginning with availability, it's important to understand the impact of tuning. Under-tuning or over-tuning systems can cause cascading trips in the process, leading to unplanned trips, resulting in low availability. Under-tuning typically generates slow and steady control, but could be too slow to respond to process disturbances, while over-tuning, on the other hand, prioritizes quick response, but compromises steady control and may even amplify disturbances. Getting this right is critical to maximize availability. Here's an example of a disturbance affecting compressor operations. With general purpose control, shown here in red, the disturbance takes time to settle and has fairly high amplitude. This has two effects. The first is the greater amplitude could result in a machine trip. For example, a high pressure limit is exceeded. Secondly, prolonged disturbances can create instability in the downstream processes. To minimize the amount of deviation from set point, a coordinated response of the anti-surge control, process control, and speed governor response is required. A general purpose control system could take up to maybe 15 minutes to stabilize the process with large pressure swings, and in contrast, a purpose-built turbomachinery control system can bring you back to set point within 2 to 5 minutes with a smaller amplitude, as you can see by the blue line, in the process swing. This increases machine availability and minimizes downtime. Not only does stable control allow you to keep your machine online longer, but it also helps you increase your yield. Consider the fluctuating flow of feedstocks. When the process is hunting for the set point, there will be unreactive chemicals creating unnecessary waste. With the confidence of stable control, risk of exceeding limits is safely reduced, and your operating envelope can be expanded to truly optimize the set point limit for greater throughput. To provide context, we could consider the compressor speed. We know that higher compressor speed equals increased throughput, but as time goes by, process resistance increases, such as intercooler fouling or hydrocarbon deposits in one or more compressor stage, and pressure limits require reduced compressor speed, ultimately lowering overall throughput. With a turbomachinery control solution, higher control speeds can be maintained by optimizing the set point limit for discharge pressure. And you can see here there's a new set point limit and quantifiable payback, increasing your throughput. Often we'll find that a wide control margin is used to compensate for slow controllers. With advanced controls, you can safely operate closer to the limit line, which means you have widened your compressor operating envelope. This enables you to close the control valve and eliminate energy waste. A good control system can match your energy consumption with your true production demands, all while providing reliable anti-surge control and protection. Eliminating manual startups can really shorten your downtime by ensuring the machine startup works the first time and every time. By fully automating startup, you can be assured that the machine will follow the OEM startup sequence exactly as defined without any hiccups. This slide shows a typical startup curve. The digital speed controller can be activated from the control room to provide a complete automatic startup. By initiating a start command, we can ramp the turbine to idle 1 for a set timestamp, move quickly through multiple critical zones, on to idle 2, and finally to the rated speed value. Now that we've covered some of the challenges addressed by advanced controls, I'd like to highlight some of the technologies that are key to realizing these benefits. First, we'll take a look at control applications. Turbomachinery control is a highly specialized application. Successful implementation and ongoing support of these systems require intimate knowledge of instrument and controls, machinery, and the process. Many OEM solutions developed are one-off, where implementation has been performed by system integrators with poor documentation on what has been done. Such solutions can result in delayed commissioning, poor support, and even a compromise in performance. In order to minimize these risks for maximizing economical gains for our customers, CTC has developed and maintained an extensive library of turbomachinery control applications. Each application is meticulously standardized and refined through 4 years of experience working with various end users and OEMs. Today, virtually any combination of a driver and driven equipment for any process can be implemented using our field-proven applications. This enables our engineers to focus on fine-tuning the system to adapt to your process, rather than spending valuable time on debugging. This is key to minimizing risks and maximizing performance gains. Another critical aspect of control application technologies is its ability to safely operate the machine closer to limits. A turbomachinery train has various limits that define an operating envelope. A simple PID-based control system will limit the operating envelope, resulting in constrained performance. So let's take an example of overspeed avoidance algorithms to highlight how advanced control algorithms can maximize availability. In this example, a steam turbine is driving a load, say a generator. When the load drops due to the reduction in electrical demands, the imbalance between the power provided by the driver and the power consumed by the driven equipment will cause the turbine to accelerate. A simple PID control system tuned for steady operations will easily reach the electric overspeed set point, leading to a machine trip. In order to avoid this undesired trip, when there's a sudden change in load, the CCC steam turbine control application implements overspeed avoidance algorithms. These will close the governor valve quickly upon reaching the overspeed avoidance line with the added open loop response. Once the overspeed trip is avoided, the PID loop will quickly and smoothly bring the speed back to the set point. Similar algorithms are found in control applications such as anti-surge, anti-choke, gas turbine, and load sharing controls, maximizing operating envelope and availability. Lastly, it is important to consider the challenge of resolving complex loop interactions. Turbomachinery controls involve very fast-acting loops that interact with one another. Consider the example of a steam turbine-driven compressor where the primary process variable is discharge pressure. When there is a disturbance in the upstream of the compressor, the anti-surge controller will open the recycle valve to prevent the compressor from surging. As a result, the discharge pressure will decrease and the suction pressure will rise rapidly. While this may keep the compressor from surging, it can introduce unsteadiness in the discharge pressure, which could result in propagation of the disturbance throughout the process. This is shown in red here. Through coordinated controls between anti-surge controller, performance controller, and governor controller, these interactions can all be minimized. As the anti-surge controller begins to open the valve, it will feed forward the information to the performance controller, then to the governor controller, in anticipation of the pressure changes. The governor controller will automatically adjust the speed set point such that the disturbance to the downstream process is minimized. This is called loop decoupling, which is shown here in blue. Coordinated controls are critical to multi-stage compressor applications such as side stream compressors often found in refrigeration services. One of the most important keywords to look for when selecting your next turbomachinery control platform is deterministic loop execution. Turbomachinery control is a time-critical application where each loop must be executed precisely at a specified interval to produce fast and smooth control responses. In this environment where control loop interactions occur in milliseconds, the requirement to design and test the solution as an entire system is paramount. By providing the entire control system, which includes hardware, software, and control applications, we're able to develop robust control solutions with global support like no other. If we think back to the car analogy, you wouldn't want to buy a Ford Fusion and try to swap out parts to make it a race car. Not that you can't, it just wouldn't compare to maybe your favorite sports car that's truly built for speed. Which brings us to the topic of speed and sensing and measurement, which deserves a short honorable mention. I just have one slide on this topic. Speed measurement has its own intricacies and must be designed with care. They are non-contact sensors that convert mechanical motion into a proportional frequency output. An optimal measurement package will include tailor-made speed gears and brackets, sensors with proper tolerance, and wiring with a high signal-to-noise ratio. There are two main types of speed sensors that are used to read speed, passive and active. The passive sensors are self-powered and use a built-in coil to generate a voltage as the gear tooth passes by. They can be used at distances up to 1,000 meters, and they're generally less expensive than active probes. Active probes are not self-powered and therefore require a 24-volt power supply source. They can be used to read speed at near 0 RPM and therefore make them a good choice for use on barrier gear logic applications. Active probes are also more forgiving for all types of gear tooth shapes. Accurately knowing your speed on the road ensures that you can make critical adjustments when needed. Even the most advanced control and speed measurement, even if you have the most advanced control and speed measurement, you're still going to need the final control element to do its job when called upon. And this is when I hand it over to Mike for more details about the importance of how precision actuation plays a critical role in the overall system.
Thanks, Emily. The next handful of slides will describe the importance of actuation precision as it relates to process controls. Many companies refer to the control valve as the final control element in a process loop. Although a properly sized control valve can eliminate cavitation and noise from a process, and the correct trim selection can extend trim life, a control valve is really just a variable orifice in a pipe. It's the actuator performance that truly provides the capability for finely tuned control. In this section, we'll give a brief review of actuator technologies that can be commonly found in turbo machinery control applications, and will offer benefits and drawbacks associated with the various types. We will then review REXA actuation technology in detail and discuss the primary applications where REXA can be found and touch on some of the key benefits that can be recognized by the plant. So there are three primary types of actuator technologies on the market. You have pneumatic, electromechanical or electric actuation, and hydraulic actuation. Each uses a different method to develop forces to create motion, all with advantages and disadvantages. We will spend a few minutes to discuss the benefits and drawbacks of each technology. So let's first spend a few minutes discussing pneumatic actuators. Pneumatically driven devices are the most common found in any processing plant. Linear pneumatic actuators are typically either the spring and diaphragm or piston type of design. For rotary applications, it's common to find both Scotch yoke and rack and pinion designs. For the purpose of our conversation regarding rotating equipment, you'll most likely find small piston type actuators controlling pilot valves on steam turbines or larger piston actuators controlling anti-surge valves. Pneumatics have advantage in the aspect that they are low cost and easy to repair, and they're a standard for most industrial maintenance departments. However, there are major performance limitations with this type of actuation because air is a compressible medium, making pneumatics subject to Boyle's law. Boyle's law simply states that the pressure of a gas is inversely proportional to its volume in a closed system. So in our actuator example, once the force of static friction has been overcome, the movement is initiated, the pressure required to keep the actuator moving is instantaneously and dramatically reduced. If the pressure is dramatically reduced, then you guessed it, the volume is dramatically increased. So the actuator is now subject to jump and overshoot due to the excess volume of air required to move in the closed actuator system. This results in hysteresis and instability. So when does this occur? This occurs every time the valve is required to move to a new position. The other component of control that's important, particularly as it relates to faster loops such as pressure or flow loops, is the effect of actuator dead time on a process. It's not the intent of this webinar to get into a full discussion on process control theory, as there's too much material to cover, but simply put, every process loop has its own time constant. Complex processes can have multiple time constants, such as turbo machinery trains and the processes that surround them. Process control engineers are responsible for calculating process time constants using complex differential equations. Any idea what the worst enemy of a process control engineer is? You got it, dead time. Going back to Emily's process control analogy with the car, dead time would be representative of driving the car with your eyes closed for a period of time. If you're only blinking for a split second, it's probably not a big deal, but several seconds with your eyes off the road, you'll probably end up in a ditch or worse. So the process controls engineer always wants to minimize the ratio of dead time to the time constant in the system. Back to our pneumatic actuator technology. One of the ways several valve and actuator companies try to improve the performance of pneumatics is through the use of smart positioners, which have been on the market for around 20 years now. Smart positioners utilize advanced algorithms that can fairly accurately predict the response of pneumatic systems. These positioners dampen much of the jump and overshoot associated with Boyle's law through slowing the jump effect. On the flip side, smart positioners greatly add to the dead time of the process loop, specifically for small step changes. This effect is accentuated under load in the process. These small step changes take several seconds to initiate any kind of response, allowing your process to move further out of control. So in a couple of words, dead time is bad. Enough about pneumatics for now. I think you get the picture. Onto electric actuator technology. As it relates to turbine control, when we're discussing electromechanical actuation, we are considering electric servo motors driving a planetary gear or a ball screw. These are also typically found on pilot valve applications, but sometimes can be found directly driving the governor valve or rack assembly if the force required is small enough. Electromechanical actuators are capable of providing faster speeds, tighter control, and better frequency response in pneumatics. There are, however, more than a few drawbacks with these actuators. The failsafe is complex or even unavailable in most cases. The thrust and torque outputs are limited to lower loads, and the electrical interface for these actuators is not particularly well developed. Many of the current actuators on the market have the added drawback that if they lose power in operation, once the power returns, they are required to stroke to the end of travel in order to recalibrate its set point position. This is a very undesirable characteristic for steam turbine control. And finally, hydraulically driven actuation. Hydraulic actuation is the standard in applications that require high performance and premium control. The technology has been the standard for rotating equipment applications from the beginning. Hydraulics offer high speeds, high resolution, high frequency response, low dead time, and the ability to configure for fail-safe capability. These benefits come with some compromises. Traditional hydraulic systems are expensive, complex, have high oil volumes, and require a good amount of maintenance. So let's discuss a typical HPU-based electrohydraulic circuit. The construction for these systems are basically all the same. All of these hydraulic systems utilize an oil tank or a reservoir and have continuously running motors and pumps that create a constant oil pressure. They utilize servo or proportional valves to drive the associated steam valves. The continuous circulation of oil generates a heat rise, which accelerates the tarnishing of the hydraulic fluid. So let's talk in a little greater detail about oil maintenance. Oil cleanliness is the real battle that we're discussing as it relates to electrohydraulic systems. Over 80% of hydraulic failures in HPU systems originate from the breakdown of the hydraulic fluid. Communication with the atmosphere allows for moisture ingress into the system, which directly leads to acid buildup. Oxidation occurs due to system heat rise. Particulate matter in the system is increased as oil deterioration accelerates. All of these systems are ultra-sensitive to oil degradation, and all of the systems are inherently dirty. So now the focus is on implementing systems to maintain the requirement of oil to ultra-clean levels. These systems are complex fluid filtration systems which are expensive to procure and even more so to maintain. Oil sampling, filter maintenance and replacement, oil flushing, and oil replacement are required to be done at high frequency for proper equipment operation and maximum uptime. Which brings us to the unique design of the Rexa electrolytic actuator. Originally conceived in the 1980s, Rexa actuation has been upgrading traditional HPU-based hydraulic technology for almost 30 years. The major points for Rexa: we have a hermetically sealed ultra-low oil volume power module, typically reducing anywhere from 95 to 99% of the oil in the system in comparison to a traditional HPU. We have no filters and require no oil monitoring or oil changes as part of a preventative maintenance plan. We have a 100% duty cycle, unlimited starts and stops per hour due to our brushless DC electrical motor. The device is extremely high precision, repeatable to 0.05% of span, regardless of the process conditions or the friction involved. We're able to provide very high thrust and torque outputs and high-speed fail-safe capability. And we have rugged, reliable construction, able to operate in temperature ranges from -40 to 250 degrees Fahrenheit. So how does it work? The Rexa technology consists of two primary components, the electrical subassembly and the mechanical subassembly. The electrical subassembly is the positioner for the actuator. This is where the main power supply and control signal are brought to the unit, and also where a 4 to 20 milliamp position feedback is available to be sent back to the CCC controller. The mechanical subassembly is attached to the driven device, typically a control valve or perhaps a steam governor rack or bar assembly. The Rexa actuator is a closed-loop system, which is different from other technologies that require an external feedback, typically in the form of an LVDT or an RVDT to close the loop. As such, the Rexa technology has both a motor power cable and a feedback signal cable interconnecting the two subassemblies. In the Rexa electrical subassembly, there is a configurable deadband parameter that can be set as low as 0.05%. When the CCC controller requests the set point to move outside of the Rexa configured deadband parameter range, oil is pumped from one side of the cylinder to the other side of the cylinder to facilitate valve motion. The actual cylinder position is continually fed back to the electrical subassembly. Once the target position is reached, the motor is de-energized and the unit holds position until the next signal change command is initiated. So let's take a closer look at the Rexa hydraulic circuit. This is the real area of differentiation with our technology in comparison to other HPU-based systems. The centerpiece of Rexa electrolytic circuit is our bidirectional gear pump, which is coupled to the Rexa brushless motor. The gear pump works in conjunction with our flow match valve, which is designated as FMV1 and FMV2 on the schematic. It's important to note from a size perspective that the flow match valve containing FMV1 and FMV2 and the gear pump can each be held in the palm of your hand. It's a very small system. When the actuator is at the desired position, the spring-loaded ball checks are in place to prevent flow of oil through the flow match valve. What allows the oil to travel from one side of the cylinder to the other is the bidirectional gear pump. When there is a signal change, the motor activates, turning the pump, which instantaneously builds pressure, allowing the ball checks to open. Oil is then transferred through the flow match valve from one side of the cylinder to the other. Once the actuator has reached its desired set point, the motor stops and the ball checks are seated, restricting the flow of oil through the system. The motor is a brushless servo motor designed for 100% duty cycle and capable of very high frequency response, greater than 5 Hertz. The cylinders that we use are dual rod cylinders, so the oil volume exiting one side of the cylinder is equal to the volume entering the other side of the cylinder. This design eliminates both the requirement for an external reservoir and the requirement for continuously circulating oil through the system. This also leads us to another significant benefit of our technology: greatly reduced oil volumes. A small Rexa system, something that would require a small cylinder for lower thrust output and shorter stroke length, like a steam turbine pilot valve application, may only have 8 to 10 ounces of total oil in the entire hydraulic circuit, including the cylinder. A very large Rexa circuit, on the other hand, one with higher thrust or torque output and longer stroke requirements, like the one driving a steam rack or lifting a bar assembly, may have a gallon of oil total in the system. So this is a far cry from your typical control oil systems, which would have a 55-gallon drum or perhaps several hundreds of gallons of oil in the entire system. As we discussed previously in the presentation, there are a couple of ideal applications where Rexa technology can be used to the plant's immediate advantage: steam turbine governor control and anti-surge valve control. Steam turbine governor control is the first application that warrants some discussion. There are a multitude of antiquated steam turbines in the industrial process market right now, with either mechanical flyball type controls, or perhaps they've been upgraded to electronic controls, but they're still relying on hydraulic systems where oil degradation greatly affects the performance. The steam turbine governor controls the steam load into the turbine casing through either a control valve external to the steam turbine or through shell-mounted control valves that could be connected to a bar or rack assembly. The steam turbine itself is there as the driver for the compressor to regulate the compressor rotational speed. The impact of poor control in a governor application creates speed instability with the turbine, as Emily was discussing earlier. Speed instability causes inefficiencies with both the turbine and compressor operation and can cause unwanted trip events, resulting in downtime of the entire train. Speed instability can also cause the unit to be required to be run at higher speeds than necessary to try to mitigate the result of swinging RPM. Rexa has both linear and rotary solutions available for this application. This brings us to our next application, which is anti-surge and recycle valves. The anti-surge valve is one of the most critical components in the compressor control scheme. First, let's give a brief description of surge. Surge is a phenomenon where flow reversal takes place due to the compressor discharge pressure increasing above the suction pressure. Surge is usually a byproduct of the process dynamics around the compressor, and surge events are common during startup and shutdown conditions, as well as when the process is operated at a reduced throughput rate. although surge events are not limited to these scenarios. When a surge event occurs, there's an immediate flow reversal that usually occurs within 50 milliseconds or so. The compressor vibrates, temperature rises, and surge events typically cycle rapidly. Surge events are damaging to the compressor. They can greatly reduce the longevity of the compressor life, causing damage to impellers, the shaft, seals, and bearings. Surge events also lower the energy efficiency of the compressor. An anti-surge valve is designed to open to protect against the surge event by allowing discharge pressure to be recycled to the suction side of the compressor. The characteristics that are important for optimal anti-surge valve performance are fast stroking speeds, high resolution and high repeatability, and minimal dead time. I don't know about you on the call here, but that sounds like a perfect application for Rexa to me. Benefits to having optimal control of the anti-surge valve are eliminated surge events. Every time your compressor is in surge, it's costing you in revenue. Extended maintenance intervals due to minimizing surge events, and energy savings due to smaller required surge margins. This allows you greater availability of the compressor map area. So just recapping some of the technology benefits with Rexa, the main one is precision of control. Again, 0.05% resolution and repeatability, which is typical of a hydraulic system that's working properly, but much tighter than pneumatic or electric capabilities. No hysteresis or stiction, regardless of the process load. Minimal dead time, the process engineer's worst enemy, regardless of the step change size. So again, with Rexa, whether we're looking at a 0.05% step or a 5% step, our dead time's consistent. And 100% duty cycle with high frequency response greater than 5 Hertz, which is important for rotating equipment applications. The other major benefits are with respect to reduced maintenance. And this is really where the hydraulics come into play because, again, hydraulic control operating the way it's supposed to operate, it's very similar to Rexa. The issue, again, is trying to keep the oil clean. We don't have to deal with that. We eliminate a high-pressure system, control oil system, and HPU and reservoir at the turbine deck. We have no oil-based maintenance required with Rexa at all. The total system oil is reduced by greater than 95%. And we use 5W50 synthetic motor oil. We don't have a specialized hydraulic fluid because our volumes are so small and we're not circulating oil. We don't require a fire retardant type of oil that's difficult to handle and expensive to handle. And in comparison to pneumatics, you don't have to worry about moisture or freezing in pneumatic control lines, and you don't have any requirement for desiccant filters. So there's a lot of advantages with our technology regardless of who you're looking at as the competition. In short, we deliver results. So at this point, the actuator overview is complete, and I'd like to turn it back over to Emily to finish the presentation.
Yep, thank you, Mike. We've highlighted some of the key challenges surrounding typical turbomachinery controls and how they can be resolved through advanced control, accurate measurements, and lastly, Mike just went through precision actuation. To help you address plan objectives, we hope we've provided enough insight into the CCC Rexa modernization package to really help you understand how we can work together to achieve more with less. I'm excited to introduce a guest speaker we have, Dave Nelson, one of our senior engineers at CCC. He will be sharing a recent case study that's a great real-world example of what we have discussed today.
Thank you, Emily, for the kind introduction. And hello, again, my name is Dave Nelson. I am an engineer in the Mechanical Retrofit Department at Compressor Controls Corporation. This case study was implemented at a US-based refinery. The project involved replacing the OEM hydraulic actuator that modulates the steam inlet control rack of a turbine-driven air blower. Now, let's take a moment to look at some of the customer's challenges. This steam turbine-driven air blower exhibited everyday RPM swings at around 100 to 200 RPMs, and at times they were as high as 500 to 600 RPMs. Manual control was the only way that the turbine would respond to a change in the speed set point. Also, dirty oil in the oil system caused the hydraulic actuator to stick and operate poorly due to contamination and varnishing of the internal components. There were also prominent oil leaks around the area of the OEM actuator pilot and power piston that were deemed unsafe, costly, and environmentally hard to contain. Another challenge was that the airflow between the problematic unit and a shared machine was unstable, and the operators were forced to make changes to the airflow by manually adjusting the blow-off valve. This resulted in a wasted energy loss to the process. Now, here was our mechanical retrofit solution. The customer contacted Compressor Controls Corporation to discuss a possible solution. We shared knowledge of the REXA actuator as a proven technology to solve the problems at their site. A REXA product demonstration was held at the customer site, and shortly after, we received a PO to implement the solution. The actuator was properly engineered and sized and placed on order. The REXA actuator and all bolt-on ready engineered adapters were then shipped to site. Once the turnaround date was established, CCC, with the help of REXA, was able to go to the customer site, remove the OEM actuation system, and finally install and calibrate the new REXA actuator and control enclosure. And the time required to do this was less than 1 day. The results of this retrofit were quite impressive. For example, the initial startup was performed for the first time ever in full automatic sequence, 0 to 100% from the control room, thus eliminating any manual control events. The performance of the turbine speed curve was now very accurate, holding steady at 1 to 2 RPMs to gain back steam cost savings. And now, with exceptionally precise control, the customer could use and optimize the load sharing features of the total train to realize additional cost savings. Oh, and by the way, remember in the beginning of our discussion when we mentioned the poor oil quality and the oil leaks as part of the customer's challenges? Well, since the REXA actuator does not require an external oil supply for operation, those oil problems fix themselves. The customer simply could get rid of the oil circuitry required by the old hydraulic actuator completely. One further note is that they were also facing nearly a $500,000 upgrade to their oil skid that supplied oil to the actuation system. This could now be taken off the forecasted budget. The capital saved could easily pay for the new REXA actuator system many times over. I hope this information was useful, and I thank you for your time today.
Thank you, Dave. At this time, I'll turn it over to Ryan for Q&A, but we wanted to point out that we've set up a landing page if you have further questions to reach out to us at the following link. Ryan?
Thanks, Emily. Just as a reminder to everyone, if you have questions, please use the question interface on GoToWebinar, and we'll try to get to them. We know we're going to go as many as we can, and in those questions that we don't get to, we'll follow up afterward. The first question comes for Mike and Rexa. It's how does the actuator fail-safe functionality work exactly?
Okay, great. Yeah, that's a good question. With the amount of time we had in the webinar, I guess I didn't really get into that. So Rexa has a standard fail-safe means by utilizing a coil spring in series with our double-acting hydraulic cylinder. And we'll utilize a high-speed solenoid that will basically allow an open circuit from one side of the cylinder to the other to allow the spring to take over as the motive force to drive the actuator to a fully extend or a fully retracted position. The only drawback with the spring technology is because it is in series, the actuators have to typically be sized a little bit larger because they're working through the process as well as through the pre-compression and the rate of the spring. And when we get into longer stroke applications, sometimes the springs become prohibitive and it's relative to envelope size. So Rexa does have an option for accumulator fail-safe technology, which the accumulator, I guess, would be in parallel to our hydraulic cylinder, would utilize a set of solenoids, and we would have an accumulator bottle with pre-charged nitrogen on one side and additional makeup oil on the other, as well as a bottle, basically a place to put the oil. And on de-energize of the solenoids, typically the nitrogen would expand and allow the oil to move through the system and bring the actuator to a fail-safe state. When the actuator needs to come back online, we actually utilize our power module to recharge the nitrogen online back up to the original nitrogen pressure, and then bring the actuator back to control from the CCC controller. So we have multiple options for that. It's very robust technology, the accumulator technology, and it's a self-contained system. We don't have to feed nitrogen in from any particular angle. So kind of a long answer, but I hope that answers the question.
I think it does. And the next one's targeted over at the folks at CCC. And what is the typical process for a mechanical retrofit?
Hey, Mike, I can take this one. Thank you. It's Dave Nelson here with CCC. Typically, we try to understand to the best of our knowledge the customer's problems at site, and we review those, as well as take a site trip to see the machine. We want to gather information like measurements and details about their existing actuator system. We then take that information back to headquarters here at CCC and work closely with REXA to size and engineer the proper actuator. Things are placed on order, and when it comes down to the time of startup, the customer turnaround, we will go to site, hold the customer's hand, and commission the unit fully. Calibration and everything is taking place at that time upon the startup. So that's basically what we do.
Excellent. Thank you, Dave. Mike, there's a question about trip times for the actuator. Could you give some detail there?
Yes. So the trip time, I guess I should have spent more time focused on Springfield in my presentation, but the trip times for the actuator are dependent upon there's a couple of factors. You've got typically these are solenoid de-energized to trip to a fail state, and there's a short amount of dead time relative to the solenoid itself de-energizing, and then it's a function of the CV through our manifold and through this solenoid itself. So typical for rotating equipment applications, we've got high-speed fail capabilities, so a lot of these will be sub 1 second, even down to 250 to 300 milliseconds in certain applications. Certainly if they want a unit to trip offline, a lot of times the governor acts as a backup for trip on the turbine. Then we would have very, very fast speeds. So anywhere from 300 milliseconds to a second is typical for what we have for trip times.
Thanks, Mike. We had a question from an audience member, and we do have some additional questions coming in, and we will try to get to all of them. And Dave, I think this one is targeted for you. What happens if the compressor discharge, what happens if compressor discharge pressure rapidly drops?
Well, we try to tune the system, and of course we do this on many places around the world, to respond very rapidly to bring the compressor back online and steady as soon as possible. So the importance of highly accurate actuation coupled with CCC technology will bring the process to stability in a fast and accurate manner.
Throwing curveballs at you, Dave. The audience questions are coming in fast and furious. Thank you all. The gentleman has a question, Mike, about the maintenance frequency of the REXA actuator, and a question about replacements and parts, and I think it's a general maintenance question.
Yeah, it's actually a good question. I appreciate that question because it's an area of differentiation against some of our competitors out there relative to being able to do field maintenance. I see the second part of that question is relative to, does it take a complete replacement? The answer is no. There's only a small amount of parts in a REXA actuator. There's 7 moving parts total. 5 of them are completely bathed in oil. The expectations for our system on a difficult application like rotating equipment would be that you'd be looking at a 5 to 7 year maintenance cycle. And typically when you go in and you're looking at doing maintenance on our system, There are O-ring seals that are part of the power module and the hydraulic cylinder, and they will wear over time, and it's really a function of how hot of an operating environment the units are in and how often they're modulating. So you can check both of those boxes for rotating equipment. You know, if you're looking at steam turbine control, you're looking at ambient temperatures, you know, typically 150 to 200 degrees, and they're moving all the time. So those applications, we're looking at a typical 5 to 7 year maintenance cycle to go in, and you'd look to replace those seals at that time. If it was a different application, some of our REX actuators have been running for 25 years out in the field. They're low-duty cycle applications in certain industries, and it's like a vacation for our product. So yes, you have the capability to maintain these in the field. It's simple to do, and we provide startup assistance and training typically with any new actuator or new customer that we work with.
We have a question. I think Dave's case study might have prompted this, so we'll throw it out there. Is there a way to calculate energy savings to show payback?
Ryan, I'll take that one. This is Emily. At CCC, we actually have a formal energy savings program with also services. What we do with the customer is we'll take a look at the entire process and work with the customer to really set up a model that defines the baseline and then the future state, so that we can measure this and keep track of what the ROI is for energy savings. We have some resources available as well, such as white papers, and would be happy to talk in more detail about that with the people that are interested, because there's real opportunity and money to be saved.
That's a great reminder, Emily. We have the on screen right now. We have the page. If you want more information, you can see the website link, and you can fill that out. We do have time for one more question, which we'll get to now, but those who we didn't get to, rest assured we are recording, and we'll make sure that folks do follow up from either CCC or REXA. So Mike, you get the last at bat here. What is the modulation time 0 to 100% with REXA, and how does that compare to a pneumatic piston actuator with a high capacity positioner?
Okay, so there's not a standard answer to this question, there's two components as you look at the mechanical subassembly that we have. We talked about the power module and the electrohydraulic circuit, and we talked about our cylinder. So depending upon the application, our cylinders can go up in size, and we always maintain typically somewhere around a maximum of 2,000 psi in our hydraulic circuit. And as the cylinder output is required to go up, we get to a larger cylinder. What we do is we get the application data. One thing that's different about REXA as an actuation company is we are very much an engineered product, even though we have a standardized design. Anybody that's done business with us knows we won't sell you an actuator off the shelf. We ask a lot of questions. We ask our reps a lot of questions. We want to engineer the product for the application up front the correct way. So we have a multiple different types of motors, from our slowest motors, which are brushless DC stepper motors, up to servo motors and booster motors, that within our standard product offering, we can go from a speed of X to 480 times the speed of X. So in answer to your question, we can achieve most speeds that you would require under modulation, and under modulation is where we're controlling with the motor. A lot of these applications are typically running at around a second per inch or somewhere in that neighborhood, sometimes multiple inches per second for fast speed of response. In the trip side, that's where it comes back to the answer on the whatever the spring force is and the solenoid force, the CV of the solenoid, to how fast we can achieve quick trip speeds. But in comparison to pneumatic positioners, our response is very standardized. One of the things with pneumatic positioners, with piston actuators, you get a relatively similar response in both directions. If you're looking at a spring and diaphragm, you've got pneumatics on one side and you've got springs on the other, and you don't have the same time constant or dead time with loading and unloading on either side of that diaphragm. There is a difference, and that allows for slop that you need to try to tune out of those actuators. But for us, we have the same dead time whether we're looking at like I said, a 0.1% or a 0.05% step as we do with a 10% step. And the difference with pneumatic actuation, because of Boyle's law, is if you have a big step, an immediate change, 5%, 10%, you're going to have very little delay. The pneumatic's going to move very, very rapidly. It's on the small changes, the very, very small changes, that a pneumatic won't even see the change if it's below, let's say, 1/4%, 0.5%. It's not going to register, or it's going to take several seconds, which brings your process out of control. So we like to say at Rexa that we're the difference. We're different than the 80-20 rule. We're kind of like the 10-90 rule as we go into a process plant. The fast applications, critical applications, these are the areas where we have a marked difference versus pneumatic technology. And that these are the areas that you should focus on. And in and around the compressor train, absolutely, these are the key applications where Rexa can make a difference. And I'm happy to answer additional questions here. I know we're losing people offline, and we've probably kind of run out of time for most people. But like Ryan said, we're happy to any additional questions that come in. We're going to review them and get back to people, and would be happy to answer any additional questions directly if you want to get in touch with myself or Emily with the contact information that's on the screen.
Perfect. Well, thank you, everyone. There are some great questions, and we appreciate your interaction. With that, on behalf of Emily, Mike, and Dave, I want to thank you for your time. And we will be sending out a follow-up email within the next couple of days, so be on the lookout for that. Thank you very much.